like to thank the organizers for inviting me here. And today, I'll talk a little bit related to some periodic L values. But I would like to say that today's talk is mainly that so far the work in progress we have is make use a lot of the Archimedean place, and we really want to kind of do more with the periodic place. So in hope that what I'll learn from this conference and from Ian Nekovar's work on periodic inputs will be used eventually at some point. Okay, so today I will talk about some joint work in progress with Frank Calegari and Vesselin Dimitrov here. And so let me just start from state a couple of, I'll call it theorem, but it's more like a list of examples about things that we want to do with a general framework. Okay, so first result is that we can talk about the periodic zeta value evaluate at 5. So this is the convergently put periodic zeta function, which here let me just give a definition in this particular case. Basically, we take the classical zeta value, the classical zeta function extend over C, and remove the contribution at 5, and this limit is taken in Q2 by definition, and the first result is this number is not in Q, so it's not a rational number. Sorry? Oh, sorry. Thank you. Yeah. And the second is more classical results. Sorry, more classical functions. So I'll put it as there exists an absolute constant epsilon, such that if we consider integers greater than 1 with the ratio mn very close to 1, they are distinct but very close to 1, then so I'll give the most interesting part is the product of the log values. And first it's irrational, and it's actually Q-linear independent with each of the factors. It just says it's we can consider product of log values of this particular shape, and the when m and n are very close. In the sense their ratio is very close to 1 with the absolute constant, then these values are Q-linear independent. And the third one is, I'll put it as one periodic analog. So there, I'll copy what I just wrote. There exists still an absolute constant epsilon prime, and such that it's not exactly an analog as the condition is slightly different. So we talk about periodic log value. So P is the characteristic, Q is P power. And so let me just I believe we don't have to assume P as odd, but let me just put it for simplicity. And with the condition to be that, so we have A over Q is what we're going to put in the log value, smaller than epsilon prime. And this is, let me just denote, this is the Archimedean absolute value. So as I said, at the beginning that our proof is actually make a lot of use of the Archimedean place. Okay, with this condition, then we have the same result. So then the product of periodic log value and the factors these are Q-linearly independent. Okay, so I'll put this as a list of examples of all things that we can prove so far, and we hope, and I'll try to explain the general framework, and hopefully we'll have a better understanding on what type of things we can prove with this setting and what type of things that we cannot.
About the condition that A and B are different.
Oh, A and B doesn't need to be. Oh, sorry. Okay, let me just say A and B are different. Yeah, otherwise it's like it only have the only relations that you expect to have. Okay. Thank you. Okay, so let me make some remarks on some history. And the first is, so the proof actually originally was, say, start from the result that the classical zeta value at 3 is irrational from the work of Avery and later reinterpretation by Berkeley. And then, so starting from there, in early work of Frank, and he kind of like did the periodic analog of the classical method, so proved that the two-adic zeta value at 3 and the three-adic zeta value at 3 are both irrational. And later on, so inspired from Frank's work, and then Berkeley did a couple of more results on the periodic, certain periodic L values. And then, so this is for one zeta value, which is kind of like the work that our work is based on. And then I'll just mention some other work on like zeta values, especially on the lower bound of linear span of like zeta values. I want to mention the work of Zuzi, Lauraville, and Fischler, and also the corresponding periodic analog in the work of Sprung, Van, Lai, and their joint work. But we are not going in this direction today. Okay. So for 2, so first is like our results, you can view it as very, very special case of the classical conjecture of Chenier, which has a lot of work in the functional transcendence case, but not much progress on the classical one. And then in a related particular situation is like there's the work of Hatta, which talk about the, okay, so I think for the rest of the talk, for the sake of like simplicity of writing, I'll just write the log product, and then, but it's understood as like this product and each factor and the one are Q-linearly independent. But I'll just write the factor to be irrational. Okay, so the work of Hatta work with the log 1 minus 1 over n and the log 1 plus 1 over n. And this one, to compare to the results, is minus log 1 minus n plus 1. I'll write this not in Q, but understood as it's a linearly independent result of the 4 numbers for n at least 4. And then so one can view this as like there's some classical input in this theorem, although this is kind of in literature seems, sorry, 50. The best bound that one could have, as far as I know. So, but it goes back to Bombieri's theorem. 54. Okay. N. Okay, so Bombieri's theorem, which says is like, so if you have one variable g function and then you evaluate at a small number when it's like, say, absolute value or periodic absolute value is much smaller than its arithmetic height, and then it shouldn't have like too many algebra relations of the value of the g function at the number, and then one can actually make it concrete into the setting. So basically, this is like a one variable situation, and for this case, is like this is a two variable situation. That's why you cannot directly apply Bombieri's theorem, but like it depends on how you kind of like relate m and n. You can get some results which. So far, we didn't be able to exactly recover what we can prove from Bombieri's theorem. I'll put there's some later inputs by Debes and Yunqing. Okay, so that's for 2, and then I'll squeeze in the for 3 remark. For 3 is like, one probably expects that Shannon's conjecture, you view it like should have a periodic analog about things should be like Q-linear independent unless you have like the multiplicative relation. And then so one still expects these not to be Q-linear independent but to be actually quite not algebraic. And then so Bombieri's theorem can still kind of like apply to certain special cases. Okay, this is an example of special case. You can do another example for the periodic setting, but still is like, I'll put it as, you can view this as periodic analog of Shannon. But we still do not know how to recover the full range of 3 using Bombieri. Of course, you can get some cases, like because the result doesn't need to work with like Archimedean places, but we just don't know how to like translate this into a one variable situation and recover this info.
So what does Bombieri's theorem roughly say? Just like
so I just said it's like you have a g function. The g function is fixed. You can work with a couple of g functions, and then the theorem roughly said is like when you evaluate at a very small value, they shouldn't have kind of like too much algebra relations among them. Small means you can work with absolute value, you can work with periodic value smaller than its height. And, yeah, not smaller than its height. There's a concrete formula. The left-hand side, sorry, something is like the absolute value is bounded by height and something related to the g function.
in general, these zeta values just not closely rational.
In general, the zeta value are supposed to be transcendence.
Okay.
And for that, okay, here when I write Andre, that's a paper by him in '96, and then here you can actually read the book by Andre in 2004, where his famous book on motives, where there's a chapter explain that if you believe the Grothendieck period conjecture for mixed state motives, then you can deduce that from that conjecture that all the zeta values at odd numbers and the zeta 2 are algebraically independent. Yeah. Okay. Okay. So more questions about the examples before I move on to talk about the general framework. Okay. so as I said, like the work start from that Frank's work kind of tried to redo Berkeley's paper in the periodic setting. So let me give a very sketchy outline of Berkeley's proof. Which of course is like closely related to a priori origin proof. So I'll start from an easy fact, and that's the part that we're going to improve today. So if we have a power series, and then, so let me just first state the easy fact in the particular setting that Berkeley stated. That's a special case of what we're going to discuss later. So it's not exactly integers, but integer with the denominator controlled in this particular way. So the bracket means the least common multiple, and the sigma is a positive integer. The easy factor states that if we consider, so for every place of Q, and we consider the periodic convergence radius of this power series, take log, take the summation, and if this sum is greater than sigma, then F is a polynomial. This easy fact can be proved using the definition of convergence radius, the product formula, and the prime number theorem. Okay, and then, so once one has this easy fact, what Berkeley did is like on the modular curve, x16, but modular out by the Artin-Lena involution, and he used modular forms to construct two power series. One is Q coefficients, the other is Z coefficients. And the Z coefficients is actually just like a weight 2 Eisenstein series. And then this one is coming from, okay, let me just make a quick remark about what it comes from. It's like, it comes from that you still take a weight 4 Eisenstein series, takes 3 times antiderivative, so theoretically get something quotation mark weight -2, takes product with something kind of weight 2, and that's the thing that you get. Okay, so such that the important part is that zeta 3 need to show up somewhere. So ax minus zeta 3 times bx has Archimedean convergence radius to be 1 plus root 2 to the 4th power. So this is like one of the identific points here. And then, so these two has like our convergence radius to be the smaller one. So this is another identific point. So basically it's like, we're going to use this trick later. It's like, so both of them, since they're coming from module form, they satisfy differential equations. And then one try to study the local monodromy so that this particular linear combination doesn't have local monodromy at this point. The first singularity it hit, and that's why its convergence radius will be larger, like the next singularity it hits. Okay, and then we're going to apply this to the simple fact. Is like if assume for contradiction that zeta 3 is a rational number, then this ax minus zeta 3 bx is a Q coefficients power series, and then we apply the easy fact. Okay, so there's a couple of things that I didn't tell you, but let me just say is that sorry. this one is z. So this one is that actually an is of form z over 1 up to n to the 3, where this 3 and that 3 is the same 3. Okay. This you can check just from the definition. And so we apply the easy effect. One thing, let me just correct myself with one. In this easy effect, you don't have to work with, I can allow to have some denominators at phi and many prime, that's fine. But in this case, you don't. So what you have is like on the right-hand side, you have log 1 plus root 2 to the 4th, because all the other convergence radius equals to 1. And then this is greater than 3. Okay, so once you have that, this tells that this ax minus zeta 3 bx is a polynomial. But from the construction, this coming from module form, you know that it should not be a polynomial. So that gives you the contradiction. Okay. So, like I said, it's related to a priori work is because that if you kind of like, so this you have some coefficients and it has a convergence radius greater than 1. It's the same as saying that if you take the ratio of an over bn, that, let me make sure. Yeah, you take the ratio of an over bn, and then the limit will goes to zeta 3 as like n goes to infinity. And that's exactly the rational approximation which coming from a priori work. And then in literature, there are lots of like attempts to prove irrationality of certain numbers, that people construct a sequence of rational approximation, but they stopped because it's like easy effect doesn't apply for those cases, and then they cannot conclude it's a polynomial and prove that the thing should then be a rational number. Okay, so this is a condition that's in the easy effect, and then we want it to we want this part to be applied to a more general setting. So you have like two things you could do: make this side larger, make this side smaller.
So what is the contradiction in the end?
Sorry?
So if you know that this is a rational coefficient, then?
If this is rational coefficients, then by the easy effect, this is a polynomial. And then you can check the exact definition, which I didn't tell you in detail from Berkeley's construction, but you can check his construction and see this one is definitely not a polynomial.
This is a module form.
It is. I mean, in the sense, this is a module form. This is kind of like a module form times the antiderivative of some module form. And then if it's kind of rational, which means this one will be a classical. Wait. Okay. I mean, in a sense, in this case, there's multiple ways that you can conclude. Essentially, it's like you will get this one to be a classical module form, and it's not.
But wouldn't zeta 3 be A0 over B0 or something like this? I mean,
so this is, sorry, the actual thing is like the coordinate x, one thing I forgot to say, the coordinate x is the coordinate here. And then, so if it's in cube bracket x, so it should be a weight 0 module form, but this one is a weight 2 thing.
X is the cube coordinate? Is cube?
Sorry, no, not the cube coordinate. X is the, just like this one is like isomorphic to P1. Oh. So that's the coordinate here. Yeah. Okay. Thank you for the question. And sorry for the very sketchy explanation, given that I didn't give you the precise definition. Okay, so back to what I said. You have an inequality which doesn't hold for many of the rational approximations that you can find in literature. And then you want it hold true for more cases. So the idea is to make the left-hand side larger and make the right-hand side smaller. Okay, so let me start from the make the left-hand side larger part, which is slightly easier. So still evangelist work, and then it's called larger radii. And also, I promise that I'll give you a more general kind of denominator type than what's written there. So thing to control the denominator type is so-called the tau invariance in the theory of G functions, which you can also find in Andre's book. Okay, so let me just actually first give the definition of the tau invariance. So we consider f1 to fm rational coefficients. Okay, here I write the rational coefficients, but you can, of course, replace Q by any number field. And also, more generally, if you look at Andre's book, you don't need to work with a one variable case. You can work with multivariable. So, okay, so let me just write Fix to be sum A and I xn. Then the tau invariance of this set of functions, power series, or you can view it as a vector valued power series, is defined to be, I'll write down the definition and explain. So here, V is a finite set of places, and then we're going to take the following is that we only care about places not in V. That's the same to relate to one, right? You can like invert at a number n there. Okay, so for places not in V, and then we're taking is the max of log plus aik v-adic value, where I is from 1 to m, and the k is from 0 to n. Okay, and the example is that in the easy fact, tau f, okay, so is smaller than or equals to sigma. Okay, and then, so basically this is the general number. So this one, sigma here I tell you to be positive integer, but this one is kind of like non-negative real number. So you can control like all kinds of like denominator types that you want.
So you exchange the order of subscript. You want A and I, and then AI. Does it mean anything? Because the I, it's
maybe in the log plus, if you just switch K and I, make it AKI.
Oh, sorry. Thank you. Yes. Sorry. Okay, now the setup is like I promised that I'm going to give you, promise I'm going to give you a larger radius. So setup is in the setup that these are the things that you are going to choose. So we have a non-negative real number which will control the denominator. So this is given. And then for every place V, we choose a map phi V from the closed unit disk to CV. This is the one with coordinate x. Oh, sorry. No, it doesn't need to be finite. You can have terrible denominators. Yes, sorry.
And when V becomes, when the finite set of primes, what is the behavior when the set of places is, when you decrease, it increases?
Yeah. Yeah, so basically it's like, sorry, I should give you an explanation. In the sense it's like, what are we doing here? It's like, you of course could sum over all the places without removing any of the V. And then that actually gives you the so-called sigma invariant in the G function. And then what you are putting back here is just the radius of convergence. You are putting back finitely many convergence radius at finitely many primes. And that will measure you like the denominator in the coefficients which you do not see from radius of convergence. If you look at the example upstairs, it's like if I just remove n, talking about things with z coefficient, but that particular denominator, then you have convergence radius to be 1 at all the places. And that's something, the denominator is something that you do not see from just looking at the convergence radius, and that's the thing that you want to measure. I can give more examples. Sorry?
So it's like a sum of the radius convergences of all of these, not in big V.
So the thing is, like, because you can pull out like finitely many places, yes. So in general, okay, so first thing is that you definitely could have convergence for, let me think for a minute. Okay, so here's the thing, is that there are 3 things in the general theory of G functions. One is this one I wrote down. There's another one called sigma. There's another one called rho. And then sigma is essentially this definition, sum over all the places, which essentially measures like how bad arithmetically this power series is. But that thing has 2 parts. One is you can measure from convergence radius. If I have something which is like 1 over, have coefficients of 1 over 2 to some power. And then you can measure it by like the periodic convergence radius. But there are certain things that you cannot measure just by looking at convergence radius, because for the above example, the convergence radius, or you think about a log of 1 minus x, the convergence radius is 1, but you still have a denominator there, and you want to measure that. And that's what the tau function is measuring. Okay. And then, so the setup is like you have something which measures the denominator. You have some other things that you want to give a generalization of convergence radius, which coming from this phi, with the assumption that 0, because I want to talk about convergence radius, so 0 maps to 0, and the derivative is not equals to 0. And then, because I want to make sure all my sum is a finite sum, so I'll just assume phi v equals to identity for all but finitely many. This is a harmless assumption in general, because if you look at the above inequality, if you have the sum of RV greater than sigma, since it's a strict inequality, you can always kind of find finitely many v, such that the sum is greater than sigma. So this is also a harmless assumption. Okay, with these 2 things, and then what we're going to consider is like we consider f1 up to fm to be Q coefficients power series, or equivalently, you can think about the Qx vector space spanned by them. And then such that condition 1, as I said, like sigma is controlling the denominator. And then condition number 2 is we want to have some convergence condition. So for every v, and then we have, okay, so you view this as a change of variable. So fi pull back by phi v is meromorphic on D01 bar. So this means it's meromorphic on a small neighborhood containing the closed unit disk for every I. Okay, then the proposition, which you can find not the exact form, but by kind of rearrange some of formulas in Andre's book, is that if the sum of all the places v And then instead of doing the convergence radius, now we do the derivative of phi v at 0. Because it's like, how is this related to convergence radius? If you have convergence radius equal to something, you just do the scaling map of your unit disk to the exactly disk, okay, a little bit smaller, where like the function is convergent, and then that gives you the derivative of phi at 0 gives you the convergence radius. So if this one is greater than sigma, then the dim of the span over qx of f1 up to fm is finite. And then so it's actually some explicit formula depending on sigma and all the phi v.
Is it clear? I mean, it is less than m. It is at most m, or you mean?
So I can, like, okay, it doesn't need to be m, so I should say dot dot dot. Sorry?
The tall you take.
Okay, here's the thing. The actual way it usually works is that you fix a sigma, and then you just say that for any finite linear combination of the set that you work with, that's, yeah.
Do you mean that phi v is defined in the neighborhood of the closed disk?
Sorry?
You write dz1 bar to cv.
Yes.
Does it mean that it is
neighborhood, small neighborhood of
it's
the,
slightly bigger?
Yeah, sorry, yeah, a small neighborhood which contains that, yeah. Yes. Okay. Other questions? So, that I'll not give you the explicit formula from if and j, and because it's like in the end of the day we want a slightly better formula, which I'll give you later. And let me first just make a quick remark. Okay, I'll just make a quick remark. I said like you have an inequality, you can make the left-hand side larger or the right-hand side smaller. Is that the smaller part, there are multiple ways to do it. I'll just point out an obvious way one could do, but I'm not going to dive into details, is that so here is like the original definition is like you work with things like all the numbers which are smaller than n. But you could replace this one by a certain range. I'll say from the range gamma times n to k to n, where gamma is something which will depend on m. Okay, so which it's not hard to deduce if you look at some version of the proof. I'll leave it here. Yeah, so this is just one definition to make it definitely work. There's some improvement one can do for the other side, which I'm not going to talk about. Okay. So here's the thing. What do we have? Is that I said there are many rational approximations in literature which do not satisfy the above condition. But now we make the convergence radius larger. So this condition is actually satisfied by many more things that you can find in literature, and people just stop there. And so let me give some examples. Okay. So I'll talk about, is it too low for me to write here? Or, okay, so I'll just say application to log product. Actually, to prove the exactly statement of that theorem, this is good enough, and which I'm going to explain. So we start from the classical rational approximation of log 1 minus 1 over n. And for reference, there are many references you may be able to find, so I'll just give one thing. So there's a paper by Aladi and Robinson.
So in the proposition of Andrea, I don't understand what the relation between the phi v and the f's, because you...
X is the coordinate. Phi v is something which you can think about is that you want to do a like change of variable from x.
Okay, but then you have some phi v, but then you make a conclusion on f.
Oh, so the f is this is so here.
Ah, okay. I didn't.
Yeah. Yeah. So let me take this as the opportunity to repeat what I said. That's important. Is sigma is the so you have two things. Sigma is the one controls the denominator, which you don't see from convergence radius. Phi v is just something which is like larger, could be larger than the classical convergence radius.
Is it phi v just scaling?
No, it doesn't need to be scaling. You could choose it to be scaling and recover the.
So
you want to choose something larger if possible, and here's the example I'm going to give.
Okay.
Yeah. Oh, sorry. Let me take this opportunity to make another remark.
So in the non-Archimedean case, the closed disk is both closed and open.
Yes.
When you say something is meromorphic or on DZ1 bar, D01 bar, does it mean that it is meromorphic in the rigid analytic disk or in some slightly bigger, with a disk with slightly bigger edges than one?
The rigid analytic disk is enough because the proof just used the maximum principle. So.
Okay, so you need the bigger
yeah.
one in the Archimedean place,
yeah.
but in the non-Archimedean it's just rigid. Okay.
Yeah. She said already before. Oh, I didn't. Sorry. Okay, so thank you. So the remark I want to make is about the disk. You don't have to work with a disk. The reason, this is my guess, okay? My guess for the reason that NJ work with the disk is, as you will see from the application later, that when you work with a differential equation, you talk about the convergence of some like formal solutions of differential equation. Disk is usually kind of the natural thing that you would work with. And in general, you don't have to. You can work with any, like in the Archimedean case, any connected domain. In the non-Archimedean case, any reasonable affinoids. And then, so for the Archimedean part, you can actually look at the reasonable work of Bost and Charles. It's kind of the most general setting that one have right now for the one variable case. And then for the non-Archimedean place, I'll write the name down so that you can more generally. So I'll write C for the Archimedean place. And it's based on early work of Bost. And the non-Archimedean place, that's the work of Bost, Chavallois, where they can give you a certain definition of capacity for like reasonable things inside the periodic curve beyond disks. Okay, so now I'm going to give the proof of item 2. So let me just say I'm going to write A to be 2n minus 1, and then we have, similar to Berkeley's proof, there are two power series. So one variable whose coefficients will depend on A, and these are like respectively solutions of 1 minus 2 this first order differential equation. The first is the solution of the homogeneous one. The second is the solution for the non-homogeneous one, such that, so this is some normalization. Okay, the upshot is that this one, this differential equation has singularities to be a plus minus a squared minus 1. And then similarly, we want to kind of like some combination of the solution which do not have local monodromy at the smaller singularity. So, and related to the log value. So, which says that h ax plus a half log 1 minus 1 over n ax has like R convergence radius to be the large singularity because the local monodromy actually canceled out. Okay, so similarly, it's like you could do, let me write b equals to 2m minus 1. So we have h ex, the corresponding formula for the other one. And then how do we kind of like take a, so the ratio of the coefficients gives you approximation of this log. The ratio of these two gives the approximation of this log. And that's why you want to take the product, and then that will give you the rational approximation for the log product. So this is actually the Adamant product. The Adamant product, so-called for like 2 power series, is just to take the like product of the coefficients. And then, so then we have h Okay, so it gives like a rational approximation of this one, and what literally it says is like, so like both this one and that one, these two will satisfy ordinary differential equations with singularities contained in, so it's a general property of Adamant product is like once you know the the singularity of the differential equation for like each of the power series, then their product, the singularity must happen within the subset, could have 0 and infinity, and then just the product of the singularities. And the other thing is like you can actually rewrite this one. Let me just do it. You can rewrite this one as h ax star with h bx plus a half log a bx then minus this is just an elementary algebra, but it shows you one thing. It tells you that, okay, so you have the convergence radius. It's like you at least have, this is a linear combination of 2 things. You at least have one factor which has the larger convergence radius than usual. So which means that this one, let me give a name called the star M and N. So the R convergence radius of star Mn is equals to, so you cannot have the smallest singularity. So you could have the small one times the big one, or the other way around. And which is approximately 1 with the assumption mn minus 1 is very small. Okay. Now is that, and this is the convergence radius. And the other thing we know is that the denominator type of this function, which you can also just get it by unwinding the definition, looks like, so if I have the k coefficients, it looks like 1 up to k squared over some integers. And the last thing is that these star mn are qx linearly, I'll put Rx linearly independent by looking at the singularities. Because like all of them satisfy differential equations with different singularities. And then the proposition, which is going to apply in this case, this is Calegari of Nj that I did right there, is so for small enough absolute constant kappa, and the qx linear span of g functions satisfying g functions f satisfying, okay, conditions. First you have the denominator condition, fx equals to this shape. And the second is that it satisfies, this is a solution of linear homogeneous ordinary differential equation with singularities with singularities very close to 0, 1, infinity. And then the last thing is that it converges over the singularities around 0. So in Rx, f is convergent over the disk around 0. Little constant, which can be made explicit. We'll see that from the proof. Yeah, okay. And then the Q span of G functions f satisfy these three conditions is finite dimensional. Okay, the proof. That's why I said I would like to give one example is how do you kind of make use of what type of phi are you going to choose? It's we consider phi infinity to be the modulo lambda function, which from b01 to c minus 1. Okay, by consider, I'll put a quotation mark here. Is that, so note that we have the only pre-image of 0 is just 0. And thus is f composed with lambda is convergent on a region. So this region actually depends on kappa. containing D01, and this region actually, I'll put curly as it converges to D01 as kappa goes to 0. Like if kappa is exactly 0, then like f will be converged on the whole thing. And then when you remove these little disks, it's like you have like you take the pre-image, it will be some region depends on kappa, and this just means that its capacity or its size will approach 1 as kappa goes to infinity. And then note, so this is the phi infinity we are going to choose. You just shrink it a little bit so that it's exactly converged. And then we'll have is like the left-hand side is
Lambda is the lambda function? No.
Yes, lambda is the modular lambda function. So its derivative is 16. And then this is approximately 2.77 something, which is strictly greater than 2. And then so it says, Andre's theorem tells you in this case, this is finite dimension. Okay, yeah. That's the proof of the proposition. And then because like all these like functions are are Rx linearly independent, if you would have like infinitely many of them to be rational, or this I for simplicity talk about this to be rational or irrational, you can kind of do another linear combination of alpha product of these things to take into account the Q linear relations. And then so it means that you could at most have finitely many pairs such that this one is rational. And then to get the theorem, you just kind of pick the epsilon smaller to rule out these finitely many pairs. But that is kind of like not very optimal, but I'm running out of time. So let me just make a remark about what's the sorry, I was squeezing the remark here. Okay, so the remark is that to remove the like finitely many, and you don't know how many exceptionals, we need a sharp and explicit. We need a sharp and explicit bound. Okay, so what we did is that instead of just copy the proof, we kind of like give a slightly different proof in hope that we're going to get as sharp bound as possible. You can also find that a related bound in the work of Bost and Charles, although in their paper they written for the tau equals to 0 case, but as Francois explained to us, you can just rework their proof, modify it, and to get some bound also with the like positive sigma. So with the sharp bound, we're able to prove theorem 1. And then for theorem 2, is so far is like we prove there's only one exceptional case that we cannot really control, but we are like in progress to also remove that one once we can get a much sharper bound. And then the proof of this one will be still using the rational approximation, but pay attention to what happens to the periodic spaces, and then that's the theorem. So let me just stop here. Thank you.
Thanks for that. Any questions?
Which function do you use for the first theorem?
Oh, so for the first theorem is that the quick answer is go read Frank's paper in 2005. That's the same function we use. And then the actual thing is that you have this one naturally coming from as the constant of the periodic Eisenstein series of weight -4, and then you pair it with something of weight 4 so that you get something weight 0, rewrite it as the powers that's of level x0 2, and then you rewrite it in terms of the coordinate of x0 2 as Berkeley did, and then that's the function f that one use. And oh, thank you for the question, because I want to make a different remark, is that in this setting, is that so you only have one function, but we want some functions. And the thing is, like, you can actually work with, if you have one function, you can work with its derivatives, because they satisfy the same denominator and the convergence condition. And for that one, it's like you work with all the possible derivatives, and then that gives you a 6-dimensional vector space, while on the other hand, is our bound gives 5.3. So contradiction.
And where does 2 come into?
Oh, 2 comes into is that so here's the thing. First, it's like x0 2. That gives you like the Archimedean thing. We also take the Q expansion. So that tells you kind of what type of Q expansion uniformization you can use. And the second thing is like the reason one use that periodic Eisenstein series is that the periodic convergence radius in that case is 2 to the 12, which is very big. You want something big, and that's the case it works out. So it's like once we plug in 2 equals to 3. Oh, I mean, these two things surely is related. Is that I think this condition is still satisfied, but like the dimension bound we have so far at this moment is a little bit weak, so cannot conclude. Yeah.
So for which values of zeta do you expect this to work? You're using some rationality of the levels of the modular curve.
So the thing is like the rationality of the modular curve. Okay, here's the thing. The part which doesn't work is that you need to make sure that first you're in this range, or unless that we kind of like weaken this one a little bit, or make this one larger, or do something else. It's like you wanted to satisfy such a bound, and then at this moment with what we have in mind, Vesselin may correct me if he has something more to say. This one will, if I work with zeta pk, that will be the k. Sorry, this is the k. And then this is like you try to be smart and put whatever thing that you want to put there. But so far it's like we get stuck at, you have a good like periodic convergence greater than 1, but one probably expects it's something like p to the 12 over p minus 1. So it gets smaller and smaller and smaller. And then the Archimedean part, so far what we can get the best is like equals to convergence radius 1. So that's why this thing will fail after finding many cases.
But so there's no theoretical obstruction to making this work for any zeta value?
There's theoretical obstructions for it. Okay, I mean, here's the thing. It's like, given this formula, and the things at this moment, we can only get this one to be 12 over p minus 1 times log p. So that's small. And that is k. K is big. Sorry, if you want to work with periodic zeta value at any large odd number, k, that'd be big. So that's bad.
So just for small p and large k?
So for small p and large k. So the thing is, like if I do 2, so this will be 12 log 2. And I think that's something, 7 is fine. 9.
There's just some small finite list of
Yeah,
pairs.
it's a
Just so fun.
Yeah. And so the thing is, like you could try, so one dream would be to work with, be smart and work with some like more than one place. We haven't succeeded in that. Yeah.
Okay, so if there are no more questions, thanks again.